Hi friends, this is Rashekar, a GATE faculty for electrical machines. Today in this video we are going to differentiate delta-delta and star-star connections. Up to now we saw delta-delta and star-star connections. In that some similarities are there and some differences are there. What are the similarities and what are the differences? Let's see here. Let's see here. Delta delta. In delta delta, the phase difference is the phase difference between primary and secondary is either 0 degrees or 180 degrees. Of course, in star star also either 0 degrees or 180 degrees. That's it. Both are same. And here phase turns ratio and line turns ratio both are x:1. Here also line turns ratio and phase turns ratio both are x:1. And here we have a delta in the primary and the secondary. Hence here we have a closed path for third harmonics, closed path for third harmonic components, for third harmonic currents, closed path for third harmonic currents. Here no path for third harmonic currents, no path for third harmonic currents, no path for third harmonic currents, no path for third harmonic currents. Yes or no? And next one, no need of modification, but here we done two modifications. One is the neutral grounding and other one is the territory winding. One is the neutral grounding and other one is the territory winding, which is delta is included because here neutral point is floating. To avoid this floating neutral, we are using a territory winding. These are the similarities and differences between delta and star connection. The similarities and differences between delta and star connection. The features of delta and star connection. What are the features? The features of delta and star connection. Let's see here. The features of delta and star connection. Delta and star connection. Let's see here. First of all, you know that here the phase voltage is equals to line voltage and the phase currents is equals to, tell me, phase currents is equals to line currents by √3 for delta. And here the phase voltage is equals to line voltage by √3 for star and the phase currents is equals to line currents for star. You know these words already. From long back you know these words, right? So now in generally the number of turns, the phase number of turns decided by phase voltage. Phase number of turns decided by phase voltage. See here phase voltage is equals to VL, but here the phase voltage is equals to VL by √3. Nothing but here 100% phase number of turns required. 100% phase number of turns required. 100% phase number of turns required. But here 57.7% phase number of turns required. Phase number of turns required. Phase number of turns required. 57.7% phase number of turns required. But here 100% phase number of turns required. Yes or no? Here only 57.7% of phase number of turns required, but here 100% phase number of turns required. The first one, very important one. And next one, here the insulation is decided by, insulation also decided by phase voltage. Insulation also decided by phase voltage, because the insulation is placed in the phase number of turns only. Hence here 100% insulation required, 100% insulation required, but here 57.7% insulation required. 57.7% insulation required. Here 100% insulation, but here 57.7% insulation required for same line voltage. For same line voltage, here phase voltage is more, here phase voltage is less. Here more insulation required, here more insulation required, here less insulation required, less insulation required. For same line voltage, here more insulation required and here less insulation required. For example, let's see here 100 volts of line voltage and here 100 volts of line voltage. Here 100 volts of phase voltage, but here 100 by root 3 times of phase voltage. 100 by root 3 times of phase voltage. Nothing but for same line voltage, here more phase voltage, here less phase voltage. Here we required, for example, for this we have to make the insulation. For this we have to make the insulation. For example, for 100 voltage, for 100 volts of phase voltage, I am taking 100 kgs of insulation. But here, how much I have to take the insulation? I have only 100 by root 3. 100 by root 3 nothing but 57.7 volts only. So here I required only 58 kgs of insulation. Here I required, for example, I am telling you just for understanding purpose. Here 100 volts of phase voltage, here 57.7 volts of phase voltage. That's why here 100 kgs of insulation required, but here only 58 kgs of insulation required. Now tell me, in which we required more insulation? Yeah, in delta-delta connection we required more insulation. In star-star we required less insulation. Listen carefully. For example, if I am taking here 100 kgs of insulation instead of 58 kgs, if I am taking here 100 kgs of insulation instead of 58 kgs, is I can increase my phase voltage or not? Because only for 58 kgs, here this is the voltage. For 100 kgs of insulation, I can increase the phase voltage up to 100 volts of voltage. Yes or no? Because for 58 volts, 58 kgs I said you, for understanding purpose. For example, I am using the same 100 kgs of insulation here also. The same 100 kgs of insulation in star-star also. If you use 100 kgs of insulation in star-star, we can increase the phase voltage up to 100 volts. If the phase voltage increased up to 100 volts, what is the line voltage? My phase voltage is 100 volts, then my line voltage is increased up to 173 volts because root 3 times increases. Yes or no? Here multiplied with root 3, this one. Here multiplied with root 3, 173.2 volts. Now listen carefully. Now listen carefully. For 100 kgs of insulation, my line voltage is only 100 volts. But here, for 100 kgs of insulation, my line voltage is 173 volts. For same line voltage, it requires more insulation. For same line voltage, it requires less insulation, 100% correct. But for same insulation, it is used up to 100 volts, but it is used up to 173 volts. Now tell me which is used for high voltage applications. Now tell me which is used for high voltage applications. The star-star connection used for high voltage applications. The star-star connection used for high voltage applications, and delta-delta is used for low voltage applications. Delta-delta is used for low voltage applications, and star-star used for high voltage applications because it requires more insulation. That's why this is used for low voltage application. Remember this point. It requires less insulation. We require just less insulation here, so cost is less. That's why we can use for even for high voltage applications also, because it requires less insulation. That's why we can use for high voltage applications. This is the difference, the first difference between delta-delta and star-star, the first features of delta-delta and star-star in terms of voltage. Just I discussed in terms of voltage. So on voltage, the dependence factors are, one is the number of turns and another one is the insulation. The number of turns are more in delta-delta and insulation is more in delta-delta. Number of turns are less in the star-star and insulation also less in star-star. But the star-star use it for high voltage applications and delta-delta use it for low voltage applications. So the discussion on voltage is completed. Now discussion on current. Let's see. Now the discussion on current. Right, sir? Let's see. Here the phase current is equals to line current by root 3. Here phase current is equals to line current. Now the conductor size depends on phase currents. Conductor size depends on phase currents. Alright, let's see here. Here the phase current is IL by root 3, but here the phase current is IL. Now tell me, at which the size is more? Here the size of conductor is less. And here size of conductor is more. Here size of conductor is less and here the size of conductor is more. Nothing but here 100% copper required. 100% copper required. Conductor nothing but copper, right? Here 100% copper required, but here 57.7% of copper required. 57.7% copper required. Here more copper, here less copper required. Yes or no? Are you okay? Because here phase current is equals to line current, and here also phase current is equals to line current by root 3. That's why only 57.7% of copper required. Here 100% of copper required. Here losses are simply less copper losses, but here more copper, that's why more copper losses. Less copper losses, more copper losses. And here less copper required, less conductor size, hence weight of conductor is less, but here weight of conductor is more. And now tell me, here less copper required and less copper losses, hence this is used for low current applications or high current applications. This is used for high current applications. And this is used for low current applications, because it requires more copper, which increases the cost. Here cost also increases. Here cost is less. That's why this is used for high current applications, and this is used for low current applications. This is simply the discussion on current. Right? So, what are the final conclusions? You have to remember. You have to remember here. The delta used for low voltage high current applications. Star used for high voltage low current applications. This is very, very important conclusion. And here EMF is sinusoidal, even it is core type or shell type. Core type nothing but 3 limbs, shell type nothing but 5 limbs. Core type nothing but 3 limbs, or shell type nothing but 5 limbs. Even it is core type or shell type, here EMF is sinusoidal because we have a closed path. Here EMF is not sinusoidal. If EMF is not sinusoidal for 5 limb shell type, because there is no closed path for third harmonics. But by tertiary winding or by neutral grounding, EMF is sinusoidal. By this modification, EMF is sinusoidal. Okay, these are the conclusions or features of delta and star connections. Are you okay? Right.